So, good afternoon, everyone. Today, I will discuss the earthquake capacity of buildings in elastic behavior. So, this is the last topic. So, what is inelastic behavior? Some structural damage is allowed during strong earthquake shaking in normal buildings, even though no collapse must be ensured. This implies that nonlinearity will arise in the overall response of buildings, which originates from the material response being nonlinear. This nonlinearity arising from the material stress-strain curve is called material nonlinearity. But sometimes the stress-strain curve may be nonlinear and also elastic, whereby on unloading, the material retraces the loading path. Structural steel has definite yield behavior and does not retrace its loading path when unloaded after yielding. Such a response is more commonly referred to as inelastic response. So, unlike sa elastic behavior, ang inelastic behavior, ito yung mga building na di na bumabalik sa dating form after the earthquake. Then, the reinforced concrete and structural steel are candidate materials for inelastic behavior. Under strong earthquake shaking, normal reinforced concrete and steel buildings experience inelastic behavior. The inelasticity is the basis for the second two of the four virtues of earthquake resistance buildings, namely strength and ductility. In this chapter, these are discussed to present the basic concepts related to the inelastic behavior of buildings. It is not possible to discuss strength only without discussing ductility and vice versa. So for the strength, lateral strength of an RC building depends on many factors including the configuration adopted, the material strength and ductilities, the relative size of structural members, the amounts of reinforcement used in members, and the strength and stiffness of joints between members. Then for the strength hierarchy, the load path in a moment frame building starts from the slabs and goes along beams, beam column joints, columns, and foundation to the soil underneath. Strength hierarchy is essential along the load path and follows the load path. Structural elements that are supporting or other structural elements and items of the buildings are required to be stronger than those that are being supported by them. The only exceptions are the connections, especially the beam column joints. And the connections should be made stronger than the column members below it. This is a special situation because in the aftermath of an earthquake, it is not easy to strengthen the beam column joint, especially reaching its interiors is particularly difficult. And often, the damage accrued in such connections is of brittle type no matter what the material of construction is. Hence, the items to be checked in an earthquake resistance building are: first, beams stronger than adjoining braces, if any. Then second is the beam column joints stronger than the adjoining beams. Then third is the columns is stronger than adjoining beams. Fourth is beam column joint is stronger than the adjoining columns. Fifth, foundation stronger than adjoining columns. And last is the soil strata underneath stronger than foundations. So when a multi-story RC building is made of moment frames that are open in the ground story to accommodate parking and infilled with masonry walls in the stories above, all the earthquake damage occurs in the ground story when it is not designed to resist earthquake effects. In such cases, the ground becomes flexible from point of view of stiffness and weak from the point of view of strength. Most of the earthquake damage is forced into the columns of that single story. So, Itong nasa figure, yung letter A, yan yung undesirable behavior with plastic hinges only in one story. So, itong mga circle sa baba, yan yung nag-indicate ng damage. So, then itong letter B, ito yung desirable behavior with ductile plastic hinges in all beams. So ang damage it is distributed in all stories. So next, the combination of inelastic hinges at the ends of beam and columns, which when formed in a building eventually makes it unstable and causes its collapse, is called the collapse mechanism. Good ductility is achieved in a building when the collapse mechanism is of desirable type. So next, this type of hysteretic loops imply good energy dissipation in building through each of the inelastic hinges at the beam ends. Such a behavior is observed in buildings that fail in sway mechanism, which ensures that beams yield before columns and ductile flexural damages occur at beam ends. This happens when the building has strong column and weak beam, in which beams are made to be weaker in bending moment capacity and ductile links, and column is stronger in bending moment capacity. So, dito, if ang building daw is built in sway mechanisms, it means strong ang column, but ang beam is weak. So, in the other hand, in buildings that fail in story mechanism, damages are concentrated in columns and that too of a single story. Here, the ductility demand on the columns is large. This situation arises when the building has weak column and strong beam design, in which columns are weaker in bending moment capacity and beam is stronger in bending moment capacity. So, dito naman, if ang building is mag-fail in story mechanism, so it means ang column niya is weak, then ang beam design is strong. So, columns that carry large axial load normally fail in compression by crushing of concrete under combined action of axial force and bending moment. Thus, they undergo brittle failure. In normal moment frames with relatively compact column cross-sections, it's become necessary to ensure that columns are stronger than beams from standpoint of bending moment capacity, and no shear failure occurs either in beams or in columns. To achieve the desired ductile action in the frame, this can be achieved by appropriately sizing members and providing correct amount of steel reinforcement in beam. Correct amount of steel reinforcement in them, and adopting capacity design principles for design of shear in both beams and columns. Such as structural configurations allow beams to dissipate large earthquake energy well before columns are damaged. So, for the beam column joints, columns are critical members of buildings. Sometimes it is not possible to eliminate damage in columns, even though of flexure under reinforced type. In such cases, their cross-sections need to be liberally proportions and designed. So next, if ang building is merong small size columns, it means it is a poor design, and ito ay also for ductility. Then, if ang building naman is large, ay merong large size column, so it means it is a good design and good ductility. So, itong picture sa letter B, so ito example ng 2000 Buj earthquake sa India. So, itong building na nasira or na-damage because ang mga columns ay maliliit. So, diagonal cracking and crushing of concrete in joint region should be prevented to ensure good earthquake performance of RC frame buildings. So, using large column sizes is the most effective way of achieving this. So, sa building, kailangan ay pinadjud ka importante is ang column design para maka-hold siya sa strong earthquake. So hanto diri lang akong report. So, thank you. So, next reporter is Miss Istorioso.
Continuation lang ni sa topic ni Karen about structural plan density. So, ang structural plan density is also called as SPD, or it is a ratio of the area of footprint of vertical elements resisting the lateral load and the plinth area of the building. So, there are percentages na gi-compare siya. So, the area of the vertical members of a building has been reduced drastically from about 50 to 60% of the plinth area in historic masonry buildings to a meager 2 to 4% in modern RC frame buildings. Then, ang SPD is a low for gravity only design of buildings, usually around 2% or lesser. And increases for gravity plus lateral load design of buildings for about 4% or more. Then, ang next is ang strength in asymmetry plan. So, there are two effects of this strength asymmetry. So, ang first is ang onset of torsional response in the building. Ang second is ang excessive deformation demand of few members. So, ang first is ang onset of torsional response in the building. So, this behavior is prominent when shaking is strong and difference in strengths is large between vertical members on either side in plane. Then, ang excessive deformation demand on few members kay nagadepend strongly on the ratio of the fundamental torsional natural period to fundamental lateral natural period of the building and the type of shaking. The next is strength discontinuity in elevation. So, ang strength discontinuity or ang sudden reduction in lateral strength of the building kay it is more serious kapag ang along the height of the building kay in plane lang na area. Tapos ang discontinuity or reduction may cause large inelastic demand at the junctions where discontinuity or reduction is present. The next is letter A. Under ni siya sa strength discontinuity in elevation. So, sa letter A or ang open, flexible, or weak stories in a building. So, di ba na may mga buildings na ginagamitan lang siya og glass para sa infill material sa ground story for the purpose sa aesthetics sa in place sa bricks masonry infills, pero naay cases na ang building kay mag-collapse siya because of using glasses, pero dili man ginatanan na building na nag-collapse siya kay nagamit sila og glasses, pero most commonly kay maujud to siya ang conclude na pag magamit og glass kay mas dali siya mas weak siya than sa bricks na ginagamit. Like for example, ginagamit siya sa first sa mga mall, then second sa mga restaurants or sa mga commercial buildings more commonly. So since kay ginagamit man ang glass more on sa ground story, diba? So pag magamit sila glass sa ground story or sa ground floor, so pag mag second floor sila hantod sa pataas, diba, kay mas more on bugat naman ang story or ang building ato, so which means na mag-weak ang sa ground floor. which is mag-cause na dito gani na mag-collapse ang building. So, for example, kay katong sa picture, ang weak story in a building, which is the collapse, open story in the 5-story residential building during 2001 Bhuj earthquake in India. So, ang ilahang ground floor kay more on glass infills material, kaya siya, pero ano man po siya, kay syempre nag-earthquake man, so murag kanang na ay contribution ang earthquake kung anong nag-collapse ang kanisya na building. So ang next is ang discontinuous structural walls in a building. So the action is similar to that of the open ground story in RC frame buildings, but this discontinuity of the structural wall is more serious than the cases discussed kaganina, which is katong na explain kaganina, because the stiffness of the wall is orders of magnitude larger than that of the RC frame with URM infills. So under sa discontinuing structural walls in a building, kay nag-compare siya og tatlo. So ang letter A is called as structural wall discontinued in ground story, or which is the worst choice. So sa letter B is ang structural wall discontinued in upper story. Also, ano po siya, an acceptable choice na gamiton. Then ang C is ang structural wall not discontinued, or mao lang siya ang pinaka the best na choice na himuon, or only option na lang jud. So sa last is ang short column effect. So short column effect arises when a column in a RC frame building is restricted from moving owing to any obstruction. So the obstruction can be, number 1, presence of unreinforced masonry infills of partial height of adjoining RC column. Number 2, conditions arising from sloping ground when some basement columns are shorter than others. Number 3 is presence of mezzanine slab which meets the columns at an intermediate height between the usual beam slab system of the floors in RC building. Number 4 is ang presence of a staircase beam or slab or K-braces on building columns which meets the columns at an intermediate height between the usual beam slab system of the floors in RC buildings. And last is the presence of a plinth beam making the height of the column below it to be shorter than that of the other column above. So, dali lang mag-end akong report. So, mag-proceed na ta sa report ni Janine. Thank you.
So, hello, good afternoon everyone. I am Janine Marie Bungolan and I'm going to discuss the ductility. So, first is the definitions of ductility. Number 1, contributors to ductility in reinforced concrete building. In a ductile building, the structural members and the materials used therein can stably withstand inelastic actions without collapse, and undue loss of strength and deformation levels well beyond the elastic limit. Isipan na lang na ang structural members sa ductile building kay murag alambre. Kung i-deform nimo, dili siya mag-crack pero dili siya mabalik sa iyang dati na form. Basically, ang pinagkaiba sa inelastic ug sa elastic kay sa elastic pag i-deform nimo ang isa ka bagay, mabalik siya sa iyang original form. So, mura siya goma. So, sa inelastic kabaliktaran kay dili siya mabalik sa iyang original form. Number 2, achieving ductility in reinforced concrete building. So, ductility in RC buildings can be enhanced ensuring the following. Letter A, choosing a regular seismic structural configuration for the building with adequate redundancy. Letter B, tune the damage to occur to predetermined the locations in members. And letter C, ensure that only a certain type of damage occurs. Lastly is the assessing ductility available in buildings. Design for ductility has not been internalized sufficiently by professional design engineers in comparison with design for the other virtues of earthquake-resistant construction. dili kayo siya gamit, it is because dili siya common samot na kay naata diri sa Pilipinas. Next is the distribution of damage in buildings. All damage of all types are not acceptable in seismic design of buildings. Damage of the desirable kind should be distributed in whole building. This ensures that number 1, more members contribute to the ductility of the building. Number 2, many members undergo inelastic deformation but each to a limited level. No one member is required to undergo excessive amount of inelastic action. Maskin pag ingnon nato na inelastic ang tanang members, we can't deny the fact na naagihapon siya limit. That's why na ay instances na mag-crack jud ang building. Ang worst kay mag-collapse ang building kay dili na niya kaya ma-handle tungod sa kusog kayo ang force na ginahatag sa iyaha. Number 3, damage is not localized to limited areas. So, dili lang sa columns, dili lang sa beam, pwede siya sa walls, and so on. Then, number 4, more members absorb the earthquake energy input to the building. So, the open ground story buildings. One classic non-example of good practice of seismic design is the way buildings in India are built with open ground stories. These buildings are characterized by number 1, the conspicuous absence of unreinforced masonry fills in the ground story and presence of the same in all story above. Number 2, the use of only brittle 230 mm by 450 mm columns with prescriptive non-ductile reinforcement detailing scheme. And number 3, the absence of any structural grade in plan of the building and some irregularities in the structural system elevation. Then lastly is the strong column with beam design or the SCWB design philosophy is critical in controlling the overall ductility of the building by distributing damage over large number of beams to achieve an ideal collapse mechanism under strong earthquake shaking. Kani siya nga philosophy kay ginabuhat para masigurado na ang damage sa columns kay ma-eliminate. It is important na make sure na inignay earthquake ang building kay dapat dili dayon mag-collapse. So, maura to tanan akong report. Thank you so much for listening and God bless.